Well, here we are together in our third week of statistics. I hope you've been having some excitement and joy working through this data set and seeing the delight that we can have looking at descriptive statistics, at graphs and diagrams of data, and moving from those graphs and diagrams toward interpreting and understanding the meaning of the data that we have access to. So in our time together this week, we're going to move from plain straightforward description more toward analysis, and I'm going to give you some of the building blocks and the concepts that you'll need to understand the analyses that you'll conduct as we move forward. So let's begin by talking about variables. We're specifically interested in the relationship between the predictor out variable, which is typically depicted on the x-axis of a graph, and the outcome variable, typically depicted on the y-axis. And in statistics, we're interested in the relationship between this predictor and this outcome. And one of the key concepts that we need to think about is the size of our sample. How many observations do we have that we're using to draw our conclusions? And so if we go back to the diagram from week 2, we'll remember that a sample is a portion of a larger target population. And in well-designed data sets and research, that sample is designed to match, mimic, or mirror the population from which it is drawn, so that as you understand things about the sample, you can understand things about the population. So as we're pulling people and observations from the larger population into a sample, one thing that's important to remember is that as our sample changes in size, our confidence in our findings also changes. So if we think of our earlier example of the number of hospitals that we have data on regarding heart failure readmissions, if we have data from 4 hospitals in the United States, our confidence that those 4 hospitals experience speaks to or represents the entirety of the United States is very, very small, as depicted here by the dot on the left-hand side of the x-axis. So this graph illustrates that when we have a very small sample size, we have very little confidence that we can trust the conclusions that we find in that sample. And as our sample size increases, we move from 4 hospitals to, say, 4,000 hospitals. Our confidence is greatly improved. We have a greater sense that what we find out about those 4 hospitals would hold true in other hospitals in the United States, assuming that our sample of 4,000 is relatively representative of all hospitals in the country. And so as our sample size increases, our confidence in the findings also increases. So when we have a very small sample size, our confidence intervals, or our variance, how much difference there are in observations around our measure of central tendency, is very large. So a small sample gives us very large confidence intervals. And conversely, if we have a very, very large sample, our confidence interval is likely to be very tight, very narrow. We're likely to have very little variance around our estimate of central tendency. This is a rule of thumb, and it certainly has many exceptions, but it's a good place to start as we think about the relationship between sample size and confidence intervals. And this depicts that information in another way. If we look at the second graph in the line, the N, or the sample, has 3 participants or observations in it, and we can see there's quite a bit of spread around that mean. When we increase from 3 to 10 observations, the mean hasn't changed, but the amount of spread around that mean has clearly decreased. And when we get to those 20 observations, that confidence interval, or that spread around the mean, has decreased even further. So we talk about the spread around the mean, the variance, central tendencies, all to help us better understand how our sample can be used to speak to the larger population. So Let's look at this in SPSS. Well, rather, before we look at that dynamic in SPSS, let's talk for a moment about confidence intervals and what they are. So if we look at this distribution of data, and we see that our mean value here is 100. Now, if we expand beyond that and look at these two bars here at 80 and 120, within this data set, 66% of all observations fall within this range. That's the definition of a standard deviation. A standard deviation is approximately 33% of the observations above and 33% of the observations below the mean value. So this is all of the observations within this portion of our graph represent 66% of all observation. That's one standard deviation from the mean. If we look at how this plays out in hospital readmissions for heart failure and the excess readmissions, we see that we have a mean value and a standard deviation. This is a standard way of reporting the measure of central tendency and the variance around it. And in our data set, for the United States as a whole, the mean readmission, excess readmission ratio is 1.002 with a standard deviation of 0.080. So what I'd suggest you do now is pause the video for a moment, open SPSS, open the data set, and see if you can get the mean and the standard deviation of this excess readmission ratio. So here we are in SPSS. Now that you've run the analysis yourself, let's look at that. If we go to Analyze, Descriptive Statistics, and Frequencies, we can select the variable of the, the excess readmission ratio for heart failure, and can scan through our variable list. Here we go, excess readmission for heart failure. Let's get the statistics of the mean and the standard deviation. That's all we're interested in at the moment. And we'll tell, okay, let's generate those data. So here we have the mean of 1.0015, just saw on the PowerPoint slide, standard deviation of 0.080. So if I take that standard deviation, add it to the mean, and subtract it from the mean, I get a range of 0.92 to 1.08. So 66% of all values around the mean number of heart failure excess readmissions fall within this range. Now let's say you're quite happy you've found the standard deviation, you've calculated the range in which 66% of all values fall. Now you'd like to know where 95% of all values fall around the mean. And that's depicted graphically here, where our mean in this hypothetical data set is 100, and two standard deviations below that mean gives you a value of 60, and two standard deviations above gives you a value of 140. So 95% of all data points are between 60 and 140 in this data set. So let's apply this thinking to our SPS analysis and see how many observations are between the mean and two standard deviations above the mean and below the mean for this excess readmission ratio of heart failures. So here we are back in SPSS, and what I'd like you to do is go to the Analyze tab, and we're going to go to Descriptive Statistics, but this time let's go to Explore. We'll see how you have some additional power for gaining descriptive statistics with this option on your menu. So let's select the dependent variable as the heart failure readmission excess ratio. So I'll select that one from my list. heart failure, readmit, to scan through, excess. That'll become my dependent variable. And I'm going to pull the descriptive statistics for that. So let's run that analysis. So here we have the number of cases from our data set of 2,993 that have data on this ratio. The mean value is 1.00, as we saw before. And this 95% confidence interval here reports that 95% of all values fall between 0.999 and 1.000 when we're considering how much confidence we have in our estimate of the mean. So this gets toward our analytic statistics, which we'll talk about a bit more later today. But that is the 95% confidence interval around the mean estimate. It's not the 95% confidence interval for where all of the observations lie around the mean. This is a measure of how confident we are about that mean, and our standard deviation is more about how much variance we have around the mean in the actual data. So if we take these data from SPSS and go back in to our discussion on this graph, we have the mean value of 1, and we add the standard deviation of 0.080. We add it to the mean, and we subtract it from the mean, and so that tells us that between 0.92 and 1.08, 66% of all values are contained. When we broaden that to the 95% confidence interval, we add 2 standard deviations to the mean, and then that will tell us how many values are above the mean and how many are below it. So as you can see, the 66% confidence interval, or 1 standard deviation above and below the mean, is contained within the 95% confidence interval, of course, because 95% confidence has a larger range of values summarized. So let's compare that discussion to a non-parametric discussion, or situations where we use the median to summarize the data. Now this graph depicts the same distribution of data, and we're assuming that we want to look at the median now. And so the median is depicted in green, which in this data set is also 100, since they're normally distributed. And the 50th percentile, the interquartile range, is from the negative 25% below the median to 25% above it. So in this data set, the area in green would be all of the observations that fall within the interquartile range. So if we apply that to the excess hospital readmission ratio, let's go back to SPSS and calculate the median and the interquartile range. Of course, there are multiple ways to do this. I've talked before about using the analyze and then descriptive statistics frequency option, but let's look at the Analyze Descriptive Statistics Explore tab for a moment. We're still looking at the excess hospital readmission rate. We're going to select 95% confidence interval for our statistics, say yes, that's what we want. And the output here shows us the median value of 0.9984. It gives us the interquartile range of 0.10. So we know that if we add 0.10 to the median and subtract it from it, we will get the range in which 50% of all observations lie. If we come back to our graph, it would look like this. We report the median and then follow it in parentheses with the interquartile range. So in summary, the confidence interval is the area in which 95% of all observations lie. And we'll talk in a moment about hypothesis testing and how we use these confidence intervals to test for differences between variables and groups. So with that, thank you so much for your time today looking at confidence intervals and sample sizes. I look forward to talking about